Here's a probability problem that is interesting because if you reduce your fraction, you'll get the wrong answer. And I just think that's really interesting because I never came across a situation like that before. Ever since we were in elementary school, we're told to reduce our fractions. So 3/6 would be reduced to 1/2, and 4/6 would be reduced to 2/3. But if you do that here, you'll get the wrong answer. So here's the situation. We have two coins in a box. Coin A is fair, probability of head is 1/2. Coin B is unfair, so probability of a head is 2/3. I forgot to include my instructions here. What we're going to do is reach into this box, blindly pull out a coin, and flip it. So what is the probability of a head? If you wanted to design such an experiment, it would be difficult to design a coin that gives you a 2/3 probability of a head. So an easy way to design this experiment is you could have, instead of two coins, coin A and B, you could have two boxes, box A, box B. Box A could have two cards in it. One would be head, one would be tail. So you would have a 1/2 probability of drawing a head when you reach into box A. And then box B would have three cards. It would have two head cards and one tail card and give you a 2/3 probability of pulling out a head card. And then what you do is either flip a coin or use a third box that's labeled A or B. And then, so what I say here, use a third box with two cards in it, and these cards are labeled A or B. So then you use your third box, you pull out either card A or B, and then that will tell you which box to use up here. Or you could just initially use box A since it has two cards in it, heads or tails, and if you get a head, then that means you draw again from box A. And if you get a tail, then that means you draw from box B. But anyways, those are the finer points. So here's what a tree diagram would look like, and this is the wrong tree diagram. You're going to reach in. Actually, I'll just use, instead of using box A and B, I'll keep it simple with coins. We'll just pretend we have an unfair coin with 2/3 head. Okay, so we reach into our box. We pull out either coin A or coin B. With coin A, we have a 1/2 probability of head, 1/2 probability of tail. With coin B, we're going to have 2/3 probability of head, 1/3 probability of tail. So if we add up our winners here, we're going to have one winner here and then two here. So it'll be 1, 2, 3. We're going to have 3 winners out of 5. And that is the wrong answer. So 3/5 probability of drawing a head in this situation is the wrong answer. And that is because 2/5 of the time, here's 2 right here, 2/5 of the time we'll be flipping coin A, 3/5 of the time we're going to be flipping coin B. And we know that's not accurate because when we blindly reach into the box and pull out a coin, half the time should be coin A, the other half the time should be coin B. So right here, what I've done is reduced the fraction. So now what I have to do is unreduce this fraction. In other words, I have to turn 1/2 into 3/6, and I have to turn 2/3 into 4/6, and I'll show how I do that and how that logic works. Here I have the correct tree diagram or flow diagram to show how to get the correct answer. All right, so we have coin A or B. We're going to pull out either one. Half the time we'll get coin A, half the time we get coin B. And then since half the time we're going to pull out coin A, we flip it. And half of that time we're going to get a head. The other half the time we'll get a tail. So I labeled this head right here as head A because it came from coin A. And then half the time we pull out coin B, flip it, 2/3 of the time we will get head B. You could follow this flow diagram either left to right or right to left to do the math on this. I'll go left to right. Half the time we pull out coin A and then we flip it, so then half the time of that we get head A. So that's left to right. Another way to say this is head A is 1/2 of 1/2. So 1/2 of 1/2 equals 1/4. 1/4 of the time we will get head A as a result. Then same thing with coin B right here. Head B is 2/3 of the total right here. So head B is 2/3 of 1/2. 2/3 of 1/2 equals 1/3. That means 1/3 of the time we're going to get head B. Now what we can do is we add our probabilities of 1/4 plus 1/3, and that will equal 7/12. Here's something that's interesting. When I add these probabilities here of 1/4 plus 1/3, In my mind, at least, there's no intuition as to why I'm doing that. I mean, why am I just adding these two random fractions? Why am I not multiplying them? And that's because my tree diagram here, it's not really representative of actually, or it doesn't really represent what's actually going on. So when I redraw this tree diagram in a more accurate manner, then adding these probabilities right here will make sense, and I'll show that later on. So what I did here is took the probability of head A plus the probability of head B equals the probability of head A or B. I don't remember the exact official way to write that in statistics or probability classes, but oh well. So I wrote 7/12 equals the probability of head A or head B. Right here is how we start to draw or put together our accurate tree diagram or probability tree or whatever you want to call it. Okay, we have 7/12 probability of getting a head, which will either be head A or head B. That means we need to have 12 permutations or 12 end results. So 7/12, 12 is in the denominator. When we reach into the box and pull out either coin A or B, half the time we'll get A, half the time we'll get B. That means out of those 12 permutations or 12 results, 12 final results, 6 of those times we should be using coin A, and 6 of the times we should be using or flipping coin B. So let's say we reach into our box, we blindly pull out a coin, and it is coin A. Then we flip it, and we get the head right here for head A. So 6 divided by 2 equals 3. That means we need 3 head A's. So you can take 6 times 1/2 to get 3, or you could take 12 times 1/4 to get 3. And that 12 comes from here because we have 12 options, and 1/4 of those times, right here, 1/4 of those times you're going to get head A. So we have 1/4 times 12, which equals 3. So we're going to have 3 head A's. Do the same logic here with coin B. Kind of messy writing there. We have 6 right here. 2/3 of the time we'll get heads, so 6 times 2/3 equals 4. That means we need 4 heads. Or you could say 12 total, because we have 7/12 right here. So we have 12 options total, or 12 possible permutations. 12 times 1/3 equals 4. So we're going to have 4 heads, and with the same math, we'll get 2 tails. So I just wrote here, 1/3 of the time we'll get a tail. So you can take 1/3 times 6 gives you 2, or you can simply take 6 minus 4, and that will give you 2 tails right there. Okay, next page. Previous page here on the left. So notice for coin A, we have 3 heads, 3 tails. Coin B is 4 heads, 2 tails. So what we can do here, we can take 3 plus 3 plus 4 plus 2, and that does equal 12. Just a way to check our work. And that's because we have to have 12 permutations, because 7/12 is our answer for the probability of getting ahead. So right here, for coin A, we have to have 3 heads and 3 tails. So we reach into our box, we pull out either coin A or B, or we reach into box A or box B. And with coin A or box A, whatever, we're going to have 3 heads, 3 tails. With box B here, we are going to have 4 heads and 2 tails right there. Now we can correctly add up our probability of heads. We have 1, as for winners, we have 1, 2, 3, 4, 5, 6, 7. So we're going to have 7/12. We could represent this as 3, right here, 1, 2, 3, plus 4, 1, 2, 3, 4, over 6 plus 6. Or we could say 3/12 plus 4/12 will equal 7/12. As I mentioned earlier in the video, it didn't really make sense, or there was no intuition as to why we add 1/4 plus 1/3. But right here, it does make sense when we add 1/4 plus 1/3. But in this form here, we're going to do it as 3/12 plus 4/12. So it's like we unreduce our fractions. We turn 1/4 into 3/12. We turn 1/3 into 4/12. And now it makes sense to add our probabilities. And what's important is we do not reduce our fraction. We do not reduce this 4/6 to 3/2. And likewise, we don't reduce our 3/6 right here to 1/2. Otherwise, we get this tree diagram right here, coin A and coin B, 1/2 head, 1/2 tail. And then for coin A, and then coin B is 2/3 head and 1/3 tail. We add up our heads here and we get 3/5. We don't want 3/5, we want 7/12. Thus, if you reduce your fractions, you get the wrong answer. And I just thought that was interesting. Here's a finer point I just thought of on how you could design this experiment as well. Instead of having 2 coins in a box, you could have 2 dice in a box. One dice or die, whichever, would be labeled as dice A. The other would be labeled as dice B. I think die is plural and dice is single from what I remember, but it doesn't matter. So dice A is going to be fair. So that means if you pull it out and you roll the dice, and then an even number could be a winner. So 2, 4, or 6 would be a winner. Then 1, 3, or 5 would be a loser. Thus, you would have a 1/2 probability of win, 1/2 probability of lose. And then if you reach in and pull out dice B, and then you roll it, and then a 1, 2, 3, or 4 would be a winner, and then a 5 or a 6 would be a loser. That would be like the tails. So 1 through 4 would be the heads, and then 5 and 6 would be the tails. And I suppose there's other ways to do this to make it even simpler. For example, you just use one dice, and you roll it, and if you get a 2, 4, or 6, that's considered box A, and if you get a 1, 3, or 5, that's considered box B, or coin B, and then you roll that same dice again, using the rules of either coin A or coin B. So it's just kind of fun to think of different easy ways to do this experiment, even if it is just a thought experiment.